Alright, welcome to my talk on Kachina, the foundations of private smart contracts. My name is Thomas, and this is joint work with my co-authors Aggelos, Kiayias, and Markulf Kohlweiss. We are all from the University of Edinburgh and affiliated with IUHK. So, to start with, I really want to revisit what smart contracts actually are. And at the most basic level, people tend to agree that they form some kind of reactive state machine. So you have a smart contract encoding rules by which other parties may interact, and in particular, rules by which they might interact with some contract internal state. And this solves the problem of how to abstract things which are out of scope, such as how to bind the real world into it. Now, one thing I do want to point out is this is quite closely related to a concept which people in computer science are very familiar with, and that is the client-server model. So you have multiple clients just talking to a server, and the server has rules governing how these clients may interact with each other. And if you start viewing things through this lens, you can see that a lot of the, or practically all of the modern internet can be seen as a smart contract. You know, if you have your eBay and you have your Facebook, and these are all rules governing the interactions of the end users of these platforms. And one note to make there is if you have these centralized systems, well, in a centralized system, you need to rely on trust for privacy. And this is also noteworthy because some of the previous solutions to adding privacy to smart contracts re-centralize the privacy aspect of them. Now, on a blockchain setting, what's more typical is that you have a chain of blocks, and the smart contract is constructed through a replicated state machine. Basically, these blocks contain transactions, and these transactions just are the inputs that a specific user gives to the reactive state machine, and every user can replicate what this state machine is doing because they see what everyone is sending to it at any point. Now, if we imagine a world where we have the same thing, but with a perfect level of privacy, we want to implement essentially this ideal reactive state machine, which is fully programmable. We wanted to have no leakage, and we wanted to have a decentralized implementation. And the last of these is a bit more vague than the others, but I'll get into that later. But as it turns out, this is actually achievable, and it's a fairly well-known sort of thing that you can use multi-party computation to do this alongside, say, a committee-based blockchain such as Algorand's. So you can just secret share inputs and secret share a contract state between each of the members of the committee, and then run multi-party computation to compute state transitions over the secret shared inputs and the secret shared state, and to create a new secret shared state as an output. There are some problems with committee handoffs and so on, but the main downside of this approach is that it's prohibitively expensive to run this MPC for any reasonable contracts, and in particular for the amount of throughput that you might want. So modern blockchain systems are already struggling with scalability, and imagine if you decrease their throughput by orders of magnitude because of MPC. So we don't really want that, and that sort of goes to one of my main points, which is, well, what do we mean by decentralization? And we had to make compromises here, and our assumption was basically that we work in the same transactional model as other blockchains, and is commonly known in the space. So you have users create transactions which essentially are a statement of intent of what they want to do on the world, and then broadcast them to the network and later potentially observe what the effect these transactions have. So we're assuming that there's no further online interaction than that. And it turns out that in this setting, there is a limit to the amount of privacy you can achieve. So unfortunately, we can't get the fully ideal setting that I just described. And to briefly go through review what the reason for this is, I'm going to go with a toy contract of the King of Ether. And in this example, So if you're not familiar with the king of ether, essentially there's a throne, you can buy this throne for an exponentially increasing price, and the previous king always gets the difference between what they bought it for and what it was sold for afterwards. So imagine a private variant of this where maybe the throne, you can bid however much you want and you don't know what the throne is worth. So if you don't bid enough, then you just lose your money. Something along those lines. And it turns out that in such a private variant, you would want to hide what the throne is worth, who holds it, when it was obtained, and it turns out that you can't really do that. And yeah, so the brief reason as to why is you can do in the transactional model, you can do a little trick, which is you can create a transaction without broadcasting it, and you can see what that would do in various different configurations of the ledger. So in particular, you can do a binary search. You can first bid a $20 value, then a $10 value, and then change again until you find what the throne is actually worth, and then you get it with that value. And likewise, you can reorder transactions to see even what the historical state of things was. Now, that's not to say that there aren't things which are solvable in this setting. In particular, the Zero Cash and Zexi papers present decentralized currencies and currencies with additional spend conditions in the case of Zexi, and they can do this essentially with perfect leakage. There are some caveats, but it's basically perfect. So for some specialized situations, there are good solutions, and it turns out they need to use some cryptographic tricks with linking commitments to commitment nullifiers to achieve this. But in practice, there are special purpose solutions, but not general purpose ones, at least not until we consider further interactions such as MPC. So ideally, if we want foundations in this space, we want something that has good foundations where these specialized solutions can be built upon, but which also, is actually achievable. So it's not a fully fledged general solution. And the basic abstraction which we propose in Kachina is to go back to the root of state machines and to make a key observation, which is that the distributed ledger is essentially a shared public state, whereas parties also do something local and they interact with a private local state, which we here represent with rho and the shared state with sigma. So in particular, you can see this reactive state machine as a state machine over these pairs of states. And when any party X is interacting with this, it only ever interacts with its own private state as well as the shared public state. So parties don't interact with each other's private states. And this is sort of in this state machine model, zero knowledge in the transactional setting is actually very powerful. So essentially we can implement any state machine of this form using just zero knowledge. And in particular, we abstracted with this diagram here in terms of the actual component which zero knowledge proofs are done about, which is here the gamma in the center, and machines which operate solely on the states. So universal machines operating on the private state rho on the left and sigma on the right. And these the central part can make queries to these machines of an arbitrary form. So essentially run functions against the state and get results from. And this constrains the central part, so the part which actually needs to be compiled into a zero knowledge circuit can be as small as possible. So you can move as much of the functionality into either the untrusted private state part or the trusted and replicated public state part. And then you need to prove, take essentially all of the query response pairs on the left as part of your witness, as well as the input to the contract. And the query response pairs on the right form part of the statement, and these are replicated when you actually put the transaction on chain. So in addition to this, we also give a methodology for using a shared private state in the ideal world, essentially to specify an idealized contract and to show that a real contract corresponds to this. And we do this for a sketch example of a private payments contract being equivalent to zero cash. And unfortunately, I'm already out of time, but I'm happy to take questions and I'm happy to discuss with anyone after this presentation. Thank you very much.